In this lesson, we are going to be looking at chemical cells and batteries. So the lesson objective for today is to explore how the reactivity of metals can be used in chemical cells and batteries. We will be looking at rechargeable batteries and non-rechargeable batteries as well. So for the first 10 minutes, we're just going to do some starter questions. And there are a number of questions. So here are the first two. And what I want you to do is open up a Word document and type your answers up. Remember to number your questions and answer in full sentences. And the first question is, what will happen in the following reaction between zinc and copper chloride? So you've got part of a word equation here. I would like you to complete that word equation, and I would like you to tell me why you get the two products. So there's 3 marks available. So you need to explain your answer. So what will happen in the following reaction between zinc and copper chloride? Question number 2. You need to explain the position of carbon in the metal reactivity series. So explain why the position of carbon in metal reactivity is important. So if you remember back to our reactivity series, the list of the metals in order of reactivity, carbon was also included in the list along with hydrogen. I want you to explain why the position of carbon in the metal reactivity is important, and that is also 3 marks. Question number 3. What causes electrical current? So what causes electrical current? 2 marks. You can define it if you want to define what electrical current is. But in a sentence or two, I want you to tell me what causes electrical current. Question number 4. Explain how metals conduct electricity. And this is 3 marks. So you need to look at the metallic structure and you need to think about how metals conduct electricity, and 3 marks are available here. Question number 5. Explain how salt solutions conduct electricity. So question number 4 was dealing with the metallic structure and how that conducts electricity. Question number 5 is asking you in terms of a salt solution. How does a salt solution conduct electricity? And that's 3 marks as well. So for questions 1 to 5, can you put the subheading starter questions, and I will give you 10 minutes, approximately 10 minutes, to answer these questions. And can you make sure you answer in full sentences, not just one word answers. Full sentences. Remember to put down the question number. And can you upload your answers back on Teams? So now let us look at chemical cells and batteries. So from the outset, we have to understand and appreciate that a more reactive metal will displace a less reactive metal from its compound. And based on this principle, we develop chemical cells and batteries. Now we're going to look at one particular type of displacement reaction and work our way through that reaction, and then we're going to see how we use that chemical reaction to build chemical cells and batteries. So that's how we're going to break it down. So we're going to break it down from the chemical reaction stage first, and then we'll go into incorporate that into a chemical cell, into an electrical cell. Okay, so the first task, what I want you to do, I want you to take 5 minutes for this. You do not need to upload this on Teams. You can do this with the notes in front of you. But I want you to take 5 minutes and look at this equation. It shouldn't really take you 5 minutes. It should take you a couple of minutes at the most. But I want you to balance and complete this chemical reaction that's shown in blue. You've got zinc plus copper sulfate, giving us zinc sulfate and copper. Now the chemical equation is not complete. I would like you to balance this equation and also see if there are any additions that need to be made to the reactants or products to make it a complete equation. So balance and complete this equation. And you do not need to upload this on Teams. Can you just put it on your notes? So just pause the video here and complete this equation. For this equation, you should have found that the equation is balanced already. So there was no need to add any coefficients. However, the equation was not complete in terms of state symbols. So what we should have here, and you should have in your notes, is zinc is a solid. Copper sulfate was given as an aqueous solution, so that was fine. Zinc sulfate, based on our acid and alkali reactions, you should also have put down as an aqueous. Let's do that again. Should be aqueous also. Copper, on the other hand, should have been placed as a solid state. So this is the equation that we're going to deal with, and this is the equation we're going to look at when we're making our cells and batteries and our primary cells and alkaline batteries, the modern alkaline batteries. So make sure you have this equation correctly in your notes, because we're going to work on this equation now and break it into an ionic half equation. So as you can see here, we have our full equation for this reaction. Now the sulfate ions are not going to change in this displacement reaction because they are considered as spectator ions. And as such, we don't need to consider them in the ionic half equations that are going to follow. So we automatically ignore the sulfate ions as spectator ions here in this, for the rest of this ionic half equation. So the first part is if you take out the spectator ions, you are left with this ionic half equation, the first one in white. So this is zinc solid plus copper 2 plus aqueous gives us zinc 2 plus copper solid. So that's our first ionic half. That's a full ionic half equation. Then what we do is we can further consider this reaction as a redox reaction as two half equations. So we can break down this equation further into two half equations. So if you're asked in an exam to write down the half equation, you need to be focusing on the red and the green segments of this reaction now. So we've gone from our full equation, our full chemical equation, which is in blue. Then we've gone down to an ionic half equation, which is an ionic equation, which is in white. And then you go down to the ionic half equation, which is in red and green. And we can think of these two latter equations as redox reactions. So one is going to represent reduction, and this is where the copper is being displayed here. So here we've got for A, we've got a reduction equation. So we say this is reduction. And what we have is copper 2 plus ions in an aqueous state will gain 2 electrons and become copper solid. Then we have the second half equation is going to be oxidation. And here we have zinc solid losing 2 electrons, becoming zinc 2 plus in the aqueous solution, and you have the 2 electrons being omitted. So we have, from our chemical cells and our batteries, because we are dealing with displacement reactions, you can derive out of it ionic equations and ionic half equations, and you must be able to do this. And I've given you an example. We've done this already in terms of redox reactions previously, so you can look back at the lessons there. But This is another chapter in chemistry where you may be assessed on ionic half equations, so you must be familiar with ionic half equations. That's why I've given you a recap or just a quick summary of ionic half equations again, and showing you that it is also turning up in this chapter as well when we're talking about chemical cells and batteries, and you may be given a question like this in your exam. So when we're talking about batteries and rechargeable batteries, which we will do with diagrams, an examination question may well ask you to write an ionic half equation for the solutions that are in the batteries. So you should be able to do that. So, in summary, the copper 2 plus ions are reduced to copper, and in the oxidation reaction, the zinc atoms are oxidized to zinc 2 plus. So I'll repeat again, the copper 2 plus ions are reduced because they have gained electrons. Reduction is gain of electrons, and the copper 2 plus has been reduced to copper. And in B, which is an oxidation reaction, the zinc atoms have been oxidized. Oxidation is loss of electrons, and what's happened is we've gone from zinc atoms to zinc 2 plus ions. Now we're going to look at the electrical cell. So you see here a diagram where two metals are being joined via a metal wire, and you can see that a lamp has been placed in the metal wire itself as well. So the metal wire is also connecting a lamp. Now, an electrical cell here is made from zinc and copper metal rods. Now, the electrons flow from the more reactive metal to the less reactive metal. Now, I want you just to think about which is the more reactive metal. This is why we started off in the starter questions with reactivity series. So just pause the video here, and I want you to think about which is the more reactive metal in this diagram. You should have deduced that zinc is the more reactive metals. So the electrons flow from the more reactive zinc metal to the less reactive copper metal. So zinc is acting as a negative terminal of this electrical cell, because it's providing electrons to the external circuit, because the electrons are going to flow from the zinc metal. So when we break down this basic electrical cell, the first thing to notice is that you've got two metals, so two reactive metals within the reactivity series that we're dealing with, joined by a metal wire. Now, once you've joined the two metal rods, here we've got zinc and copper with a metal wire, we dip the rods into a salt solution or an electrolyte solution, and in this case it's a salt solution, but you can use dilute acid. Now, electrons will start to flow through the wire from the zinc to the copper. So without doing anything now, you're not going to supply electricity or anything like that, but just by the process of dipping the metal rods into the electrolyte, what will happen is that the electrons start to flow through the wire from the zinc to the copper. So can you just take this down, please? Can you take down these basics of an electrical cell? You're going to add to it as we go on. But the first steps is that you take two metal rods, you join it via a metal wire, and then you dip the metal rods into an electrolyte solution. In this case, it's a salt solution, but you can also have a dilute acid solution. And electrons will start to flow through the wire from the zinc to the copper. You may be wondering, why do we have a lamp in the wire loop? This is to actually tell us that electrons are flowing, or we have a complete circuit. Because if we have a complete circuit and the electrons are flowing, this lamp will light up. So it's an indicator for us as well. So now the next points, what we have to note down is that zinc atoms, so now in terms of describing the process, what's happening, zinc atoms donate electrons via the connecting wire to the copper 2+ aqueous ions. If you remember back to our equation, we had copper sulfate aqueous. So we have copper ions in an aqueous solution. And what happens is that the zinc atoms in the zinc rod donate electrons via the copper wire to the copper 2+ aqueous ions. The zinc is acting as the negative terminal of the cell, because that is where the electrons are emerging from and going into the wire. This flow of electrons is an electric current. So this was one of the starter questions that we came across. So the flow of electrons is an electric current. The current will flow in the circuit, in this cell, until one of the reactants, either the zinc rod or the copper 2+ aqueous ions, is used up, is completely used up. Because what will happen is, if the zinc atoms are continuously losing electrons one after the other, eventually you're not going to have any more zinc atoms. So until the zinc solid is used up, or the copper 2+ aqueous ions are used up, until that happens, the current will continue to flow in this circuit, in this cell. So can you just pause the video here and can you jot down these following steps? It needs to follow on from the previous steps. So the reason that we have this electrical cell, or this cell working in this manner, is because metals tend to give away electrons to form positive ions. Now, the greater the tendency, or the greater the capability of the metal to form positive ions, i.e. give away electrons, the more reactive the metal is. And you can refer back to the reactivity series to look at which metals are more reactive than compared to other metals. So you can refer back to the reactivity series to see that list. But what you need to know in terms of this electrical cell is that the copper 2+ ions are accepting the electrons from the zinc atom and change into copper atoms. So can you pause the video here and can you take down these points here? You can see on the diagram as well that I've swapped around the electrodes, but it does not make a difference as long as that the arrows are indicating which way the electron flow is, and then you should determine which is your negative terminal and which is your positive terminal. And here they're using hydrochloric acid, a different solution, to make sure that the circuit is complete. Now, in terms of reactivity, so we are basing our the metal rods and the selection of the metal rods based on the reactivity series, because this impacts how the voltage will be from the cell that we are using. And what we say is that the greater the difference in the reactivity between the two metals used, the higher the voltage produced. So referring back to your reactivity series, we have a list, and you can see what the metals which are near the top of the reactivity series, i.e. your most reactive metals, and then we have your least reactive metals towards the bottom of the reactivity series list. So the greater the difference between the two metals used, the higher the voltage that is produced. And this difference can be seen as the power of a particular metal to act as a reducing agent. Now we'll look at commercial batteries. So we've just seen how a simple electrical cell can be made with different metals and an electrolyte solution and a piece of wire as well. Now we move on to the commercial batteries. So the first batteries were called primary cells. They could not be recharged, and the electrodes were made of zinc and carbon. Now if you refer back to your reactivity series, you may have noticed that carbon was also included in the list. So we make use of the position of carbon in the reactivity series. Well, it was made use of, and the initial batteries, which were called primary cells, the electrodes were made of zinc and carbon. And you can see in this diagram how some of these early batteries or early cells, primary cells, were constructed. So if you just want to take a look at some of these early primary cells, you can see how they were constructed and how they would have been used. Notice how they're trying to make use of the electrolyte solution and the two metal rods and completing it within a circuit. Some of them it's not so clear. Some of them they're encased, but in some of the diagrams you can sort of work out where the electrolyte solution would be and where the two rods would be. Now let us move on to modern batteries. Now modern batteries are also made of zinc and carbon in terms of the rods that are being used. And what we say is also that they are alkaline in nature. Now they also cannot be recharged, and these are called dry cells. And with the electrodes made up of zinc and carbon, they are non-rechargeable and they are the modern alkaline cells. But these cells produce a larger voltage than the primary cells. And once the reactants have run out in this cell, and you can see the diagram on the screen showing you where the reactants would be. Based on our equation before, you should be able to identify the reactants. Once the reactants have run out, the cell stops working, and then you need to dispose of the battery or recycle it. So these cells are also made up of zinc, and there's a carbon rod here, and it cannot be recharged, and these produce a larger voltage. And once the reactants have run out, and the reason they can't be recharged is because once the reactants have run out, the cell will stop working. So this is, the diagram is showing you a zinc carbon dry cell, and it produces a voltage of about 1.5 volts, but it cannot be recharged. And one of the disadvantages of these types of cells is that it can leak if it's left in a plant. So you may have seen this when you open up your remote control or an electrical, let's say, device which requires batteries, and you've left a battery in there for a period of time. You open it up and you may have seen a discharge coming from the batteries. So after a long period of time, the batteries can leak. So this is a disadvantage here for the dry cell. So in summary, metals tend to lose electrons and form positive ions. When two metals are dipped in a salt solution which is joined by a wire, the more reactive metal will donate electrons to the less reactive metal. The greater the difference in the reactivity between the two metals, the higher the voltage produced by the cell. Refer to carbon in the reactivity series and you will see which is the more reactive substance in comparison for the two components in the cell here. So can you just take this down for the modern batteries, just a summary of what a modern battery is, and you can quickly sketch a diagram or you can take a screenshot of this cell and include it in your notes. task now, and you're going to take 15 minutes for this, and you're going to answer the questions and upload them onto Teams. And can you number your questions, and can you answer in full sentences? So not just one word answers, full sentences, please. So you've got 3 questions here. First one, why is it not possible to make an electrical cell using 2 electrodes made of zinc metal? That should be straightforward based on what we've discussed. Question 2, an electrical cell is made using the metals iron and zinc as the 2 electrodes and a salt solution as the electrolyte. You're going to draw a diagram of the electrical cell setup with a lamp in the external circuit. So what does it mean by external circuit? Where would you put the lamp if you were to put it in an external circuit when we're talking about an electrical cell which is being made? B and C, I want you to name the metal that is reduced in the cell. C, explain which metal will act as the negative terminal of the cell, and that should be easy in terms of explain which metal will act as a negative terminal of the cell, and include 2 half equations in your answer. If you're not able to do that, okay, I can understand if that's going to be a bit difficult, but you should be able to explain which metal will act as a negative terminal of the cell. And if you can you include 2 half equations in your answer? And you should be comfortable with the word half equations. And finally, using the diagram here, which says figure 3 on the right hand side of the screen, using figure 3, explain 2 disadvantages of using zinc carbon cells compared with other modern cells. So you might have to do a bit of research on this one as well. So using figure 3, explain 2 disadvantages of zinc carbon. I talked about one disadvantage. See if you can think of another disadvantage of using this. Actually, we did mention it. It's within our explanation of today's lesson with the zinc carbon cell. We've actually talked about 2 disadvantages here, one indirectly. So can you take 15 minutes to answer the questions, upload your work onto Teams? Remember to number the questions and write in full sentences. The final task for today is going to be a research task. We've so far talked about non-rechargeable cells. Cells that cannot be recharged. Once you use it, you cannot use it again once the reactants have been used up. You are to research how a cell can be recharged, i.e. a rechargeable battery. Outline how a cell can be used over and over again. So I want you to look at the basics of what a rechargeable cell is doing for it to be used over and over again, and I would like you to include a diagram, and you may want to look at modern rechargeable batteries that you can buy in shops. That might be a place to start in terms of looking at how they work. So you are to research how a cell can be recharged. So far we've looked at non-rechargeable cells. So what the mechanism of a non-rechargeable cell is what we've looked at. Using the same basic premise, I want you to research now how a cell can be recharged, and I want you to outline how a cell can be used over and over again. I want you to include a diagram, not more than 1 paragraph, 2 at the most, 2 paragraphs, just outlining how a rechargeable cell works with a diagram. 15 minutes for that task, please.